Hello everyone. In this presentation, I will talk about our work, 3D GUT, enabling distorted cameras and secondary rays in Gaussian splatting. In this work, we first enable arbitrarily distorted cameras and complex time-dependent effects for 3D Gaussian splatting. Then we enable the generation of a unified representation for both rasterization and ray tracing, making secondary ray effects possible. To understand our first contribution, let's take a closer look at how 3D-GS performs Gaussian projection. 3D-GS uses local affine approximation to compute Gaussian projections. Specifically, we need to first find the accurate center of the projected distribution, and then use the first-order Taylor expansion of the projection function to linearize the projection process, so that we can approximate the 2D covariant matrices, sigma prime. However, a linear Taylor expansion does not work very well when the projection function P becomes highly nonlinear, so we need a more general method. We draw inspirations from the classical literature of unscented Kalman filter, and from that, we can actually approximate the 3D particles using a set of sigma points. These sigma points can be projected exactly, and used to re-estimate the 2D covariant matrix accurately. Our second contribution is, we want to reunify rasterization and ray tracing. Our solution is to perform Gaussian evaluation in 3D. This method actually works very well with unscented transform. For example, for fisheye camera, the projected distribution is highly distorted, so approximating it as a 2D Gaussian is not a good idea. But we can still compute its coverage loosely and trace rays into the workspace. In the workspace, particles are always perfect Gaussians. Therefore, we can easily evaluate them and perform rendering. Similarly, for rolling shutter camera, different pixels have different poses. So a 2D Gaussian is also a bad approximation. But tracing rays into the workspace solves the issue. Finally, unscented transform is not differentiable, but we can achieve it with ray tracing. One stone, two birds. The only downside is, evaluation in 3D is a bit more costly, as it requires 4 extra atomic operations per ray and particles in the rendering phase. Now let's look at how well 3D GUT works. For fisheye camera, we compared with fisheye GS, which is a linearization-based 3D GS extension. Our method delivers significantly better performance across all matrices, especially on regions affected more by distortions. Next, we look at rolling shutter and compare projection qualities between unscented transform and linearization. We can see that linearization can lead to obvious artifacts if there is no additional corrections. Next, we look at performance. Here, we highlight the average pre-processing latencies as well as the overall inference latencies on the MIPNER 360 dataset. Our method produces similar quality as ray tracing-based methods, but is way more efficient. However, it's still slower than 3D-GS in the pre-processing phase due to UT overheads. Finally, we want to also achieve secondary ray effects. As mentioned before, by evaluating Gaussians in 3D space, 3D GUT can get a similar formulation as 3D GRT. But there's one issue. 3D GRT integrates Gaussians in BVH reversal order. But for our method, Gaussians are integrated in depth sorted order. They are not consistent. Our solution is to perform per ray resort of Gaussians using a K-buffer, inspired by the recent work Dopplerpop. Then, with all that, we can finally achieve secondary ray effects by having a hybrid renderer, combining both rasterization and ray tracing. In this renderer, we just need to have all the primary rays rendered by 3D GUT and the secondary rays rendered by 3D GRT. The final results are convincing. That concludes my talk. Our code is accessible on GitHub, and we also enable 3D GUT in Gsplat as a plugin. Thank you.